Section 4.4 is our first section for optimization. Today we're going to talk about relative extrema and absolute extrema and identify both of those on graphs and then learn how to find them analytically. So given a graph or an equation on a specified interval, we're going to find absolute extrema if they exist. So let's talk about what absolute extrema is, and we'll compare it to relative extrema so we get a good sense of which one is which. In this first example, you're looking at 4 different graphs here. We're going to look at each one of them and talk about the extrema in the graph. The first graph that you're seeing actually has no extrema in it. If you're trying to find any sort of relative extrema, remember you're looking for some sort of a peak or a valley. You don't have that in this case. And if you're thinking like, well, it technically gets really high, right up here close to the y-axis. Yes, but there's an asymptote here. So asymptotes can't possibly represent extrema. And then you're seeing that the graph looks like it approaches the x-axis, but it never actually touches. So we would say that for the first graph, we actually have no extrema at all, which maybe is a weird concept, but it doesn't have any extrema. It does have a vertical and a horizontal asymptote. So the vertical asymptote is at x equals 0, and the horizontal asymptote is at y equals 0. We want to bring that terminology back in today. Now, number 2, this is the type of graph that we saw a lot of as we were working through the first 3 sections here. So we can see 3 obvious places where we have either hills or valleys. So if I'm looking at this value down here, I know that I have this relative minimum. And then I know I have another relative minimum over here at the other valley. And then there's a relative maximum at the top of this hill close to the y-axis. That'll be a relative maximum. What I'm looking for now is I'm trying to determine if we have any absolute minimums or maximums. An absolute minimum or maximum is the absolute smallest and largest value obtained on the whole graph. Now, it's sometimes a little bit trickier to find this, but one thing that might help you here is if you put some arrows on your graph. I should have put them on here for you, but we're assuming that this graph just continues to head upwards on the left and the right. When I'm determining if I have any absolute extrema, I'm looking for, let's say I'm looking for a relative minimum, for instance. If I'm looking for an absolute minimum. If I'm looking for an absolute minimum, I'm looking at the absolute smallest value that the graph can possibly attain. I tend to scan my graph sort of from bottom to top if I'm looking for an absolute minimum. And I'm seeing what is the absolute lowest point on this graph. Well, if I scan it from bottom to top, I'm going to hit this first value that we chose as a relative minimum. A relative minimum can also represent an absolute minimum. So in this case, we have an absolute minimum at our first relative minimum. And that's because it's the smallest y value that's actually on this graph at any point. Now, if I was to look at an absolute maximum, again, I could scan this and I would want to scan this all the way up to the top. Notice, however, that you're never actually going to hit a highest value because this graph continues to head up towards positive infinity as x continues towards negative and positive infinity. The y values continue to increase. So there's actually no absolute maximum on this graph. I'm going to say there's no absolute max. So we can't actually attain a highest value here because the graph heads off towards infinity, but we can attain a lowest value. So notice that the first relative minimum actually represented an absolute minimum, whereas the second relative minimum is just a relative minimum. It doesn't mean anything else. It's just a relative min. Nothing else we can do with that. Looking to graph 3 now, I have to be a little bit more careful with this graph. The reason being, Graph 2 had arrows that we put on there indicating that that behavior was going to continue. With graph number 3, we just have a segment of a curve, so it cuts off. But again, you can do a quick eyeball scan here and determine where you have relative extrema. So I'm looking for the top of a hill or the bottom of the valley. So as I'm looking here, I'm noticing right away that it looks like I have a local or relative maximum up here at the top of this hill. And then again, I have, if I look to the bottom, the lowest point that I'm seeing right now is the relative minimum at the bottom of this hill. All right, so those would be the two relative extrema. Now, if you're looking at these other 2 points and wondering if they could be relative extrema, remember that you're not going to get relative extrema at endpoints. You have to, if you're at the top of a hill, for instance, you have to be able to go around to the other side. If you're at the bottom of a hill, you need to be able to come back up. So there has to be a neighborhood around that point. And in this case, we don't have that. So we can't call the endpoints relative maximums or minimums. We can look at them and try to determine whether we have absolute mins or maxes based on those endpoints. So again, I'm going to think about this graph as I go from bottom to top. That's just the way I usually like to see these absolute extrema. So as I'm going from bottom to top, the absolute smallest value that I hit on this segment of the curve happens here at the relative minimum. That's actually the lowest y value. Sometimes our eye wants to get pulled over here to this direction, and our eye wants to say, like, wait, this is the smallest point. But we need to be really careful and make sure that we notice that there's another y value over here that's smaller, and it's at the relative minimum. It's not at the end point. So we're going to say now that this relative minimum that we have on this graph is also going to be the absolute minimum. Also. So it represents both. Now, as far as your absolute maximum, we're going to keep scanning the graph, and then we're going to go and we're going to find our absolute highest y value to get to the absolute maximum. So as I'm scanning this up, I'm going, oh, I'm looking, okay, now I've hit the relative max, but I have another y value that's even higher, and that is at this right endpoint. Now, I know that we said that the endpoints can't represent relative extrema, but they can represent absolute extreme values. So in this case, I would say that this upper or right endpoint represents an absolute maximum. And again, that's because the graph cuts off here. If it had an arrow on it, I wouldn't be able to say that was an absolute maximum. I would say the graph had no absolute maximum, but it does not have an arrow. It has just a point. So that's not going to affect us in any way. You might just want to make a note to yourself in case, just because I know students struggle with this. You might want to note that this left endpoint is not a relative extreme because it's an endpoint. So we can note that. As far as the fourth graph is concerned, we can look for relative extrema first because that's going to be the first thing that's easy to spot. Now, it's a little bit harder to spot those for graphs that don't have that traditional curvy shape. So we'll still look and see if we have this relative extreme value. But again, we're looking for relative extreme values to have neighborhoods around both sides, and we want to be able to clearly see that we have either a hill or we have a valley. Now, in this case, I would say that I don't actually have any relative extrema at this point. Oh, well, actually, no, we can say that the top point, sorry, I almost mislabeled this for a second. This top point would actually be a relative maximum value on the graph. As you're looking around on both sides, we do have a neighborhood around this point. We could say that in that neighborhood, we do hit this highest value here at y equals 4. and then it gets lower again. Now, you also are probably noticing that if you were to scan this graph from bottom to top, if I was to scan this graph from bottom to top, I would notice that I have this absolute minimum value here at the right-hand endpoint. So my absolute minimum would be this point down here. Absolute minimum. And then my absolute maximum value would actually be the same as the relative maximum value here at the top. Because if I was to scan this graph from bottom to top, of course, the first point I hit, we already said was the absolute minimum. If I go up further, I hit that next endpoint, but that next endpoint isn't really doing anything for us. It's just somewhere in the middle of our scan. So you continue to go up, and then you get to this highest point on the graph at the absolute and relative maximum value. So that's sort of how this works. And again, this left endpoint represents nothing. It's an endpoint, and it is somewhere in the middle. It's not an extreme value. So we wouldn't have to say anything about it regarding extrema. All right, so here's our observation. On a closed interval of a continuous function, now a closed interval, if you'll remember, just means that we're cutting off the endpoints. If I'm talking about a closed interval of a function, I'm saying my function goes from A to B, and we're thinking about that on the x-axis. So that means that we have a clear starting point and a clear ending point. And same idea with 4. Starting point, ending point. So that this is a closed interval. There will always be absolute extreme. Now, we're always going to have absolute extreme because we don't have a case where we have these arrows that are sending the graph up indefinitely or maybe down indefinitely. We don't have that problem. And because it's a closed interval, I also don't need to worry about a situation like this. I mean, at some point, there's going to be an absolute minimum or maximum value no matter where I cut this off. So that's an observation that you can see based on the graphs that we just discussed. Now, your extreme value theorem states that if f of x is continuous on a closed interval from A to B, then f has both a minimum and a maximum on the interval. So it's got to be continuous over the interval. One thing we do want to be careful about is this graph for number 1 is not going to be continuous at 0. So we'd have to be really careful about what we said about that interval. Another observation is that these absolute extrema occur at relative extrema or endpoints. Okay, so in both cases, we had that happen where our absolute minimums and maximums also coincided with relative maximums in some cases, or they coincided with endpoints in others. Okay, thus, for a function that's continuous on a closed interval from A to B, which is what we're going to be focusing on today, just chopping that off and talking about a closed interval mostly, we will expand that out for an example or two. Here's what we're going to do. Here's our process. Absolute extrema on a closed interval from A to B. The first thing we're going to do is find critical numbers of f, where, remember, this is where f prime of x equals 0, or f prime of x does not exist. Then we're going to evaluate each critical number in the interval because we know that the critical numbers are possibly going to yield relative extrema, and we know that relative extrema could possibly yield absolute minimum and maximum values. So we're going to evaluate the critical numbers in the interval and the endpoints because we know that the endpoints are another place where we might have these extreme values occurring, absolute extremes. So the largest value we find when we evaluate our function is going to be the absolute maximum on the interval, and the smallest value we find is going to be the absolute minimum on the interval. And that's going to be our process today for finding absolute extrema on a closed interval. So we're going to do that first. I think that students generally tend to do very well with this. It's kind of just like a little extension of what we were doing previously in the first section. I'm just going to move my screen a little bit. A little close to the camera. Okay, there we go. Excellent. I'm gonna put this here. There we go. All right, example, find the absolute extrema on the closed interval. Let's do that. It's like this comedy of errors. All right, example 1. F of x is going to be x squared divided by x squared minus 9. What we're going to do is we're going to look for absolute extreme values on the closed interval from -2 to 1. So I'm thinking about what's happening with this graph, and I need to be considering what's happening on this particular interval. One thing you might want to notice is that the denominator, x squared minus 9, excludes the values negative and positive 3 from x. So if x is plus or minus 3, the function's not continuous. Notice, though, I gave you an interval where that's not going to be a problem for you, because I can't really ask you to do this where the function's not continuous. So if we were to talk about looking over the value plus or minus 3, we'd have a problem. But we are not looking at an interval that covers either of those values. We're inside those values. So it's not going to be a problem for us. So we always need to just make sure that the function's continuous. I'm going to write down what I just said, because the vertical asymptotes occur at x equals plus or minus 3. F is continuous on the closed interval from -2 to 1. So in order for us to be able to apply this, in order for us to use this process, it has to be the case that our function's continuous on the interval. So we're good here. All right, the one thing we're going to do, I should have kept this out, but let's look back at our directions. It says to find critical numbers of f where either the derivative equals 0 or it does not exist. That's the first step. So this is going to start out kind of like what we did in 4.1, just finding critical numbers and looking for the relative extrema so that we can determine if the relative extrema are absolute extreme values. Right, f prime of x, we're going to use the quotient rule here. F prime g minus f g prime, all divided by g squared, and then we'll simplify. So we have 2x cubed minus 18x minus 2x cubed divided by x squared minus 9 squared is negative 18x divided by x squared minus 9 squared. This is our first derivative. We're going to check the first derivative to find our critical numbers. Now I'm looking for places where f prime of x either equals 0 or where it doesn't exist. Let's focus on 0 first. I'm going to take the numerator in this case, which is negative 18x, and I'm going to set it equal to 0. When I divide both sides by negative 18, I get x equals 0. Keep that. And then the other thing we're going to do is we're going to look for values that make the first derivative not exist. So I'm going to take x squared minus 9 and set it equal to 0, which means x squared equals 9 and x equals plus or minus 3. You've seen this before. Again, these were vertical asymptotes. So if we were to do a sign analysis, I would want to consider these values, but I'm not doing a sign analysis, first of all. So I'm not going to be considering these as critical numbers. They can't be places where we have extrema if they're vertical asymptotes. Vertical asymptotes, not critical numbers. That's really important to note. Another thing, though, to consider is that these values, even if they were going to be used as critical numbers, they can't actually be used as critical numbers because they're not in the interval. We're only looking at values of this function where x goes from -2 to +1. These values are not even in the interval, so we don't even need to worry about them. So I'm going to make a second note about that, actually, because I know these don't apply, but I also just want to make sure we note that they're not in the interval. I'm going to say that they're not in -2 to 1. Also. Excellent. So now we have the first derivative. We set it equal to 0. We got a critical number. We took the first derivative, made sure we looked at values where it did not exist. We don't have anything important there. Notice that 0 is inside your interval. Check. If it's not in the interval, then it's not going to matter to us. We're only looking at values inside the interval. Okay. All right, now that we have this, the next step is to evaluate the function at any critical numbers or endpoints. So what I usually do for this is I start out, remind you of the direction here, evaluate each critical number in the interval and the endpoints, and then we'll determine which value is the largest and which one's the smallest. So I'm evaluating the function now. I'm trying to find the y value at x equals 0, x equals -2, and x equals 1. It's up to you the order in which you decide to do this. I like to just leave it in order from smallest to largest. So I'm going to evaluate the endpoint, and I'm going to determine the y value there to see how large or small it is. Then I'm going to move up to my critical number, which is inside the interval, and then I will use the endpoint. So the endpoint is 1. I have one more example I'm going to put in below this. So if you're trying to space things out, you might want to write a little bit smaller, but also feel free to use the other side of the page. Okay. I'm changing things up, so I should switch my color. All right, so I'm going to look for the function evaluated at these values. Now, if you would like to put this into your calculator, that is absolutely fine. I will not fault you for that. So your function here is x squared. Oh, I think I had something just like that in my calculator. I should have left it in there. Divided by x squared minus 9. The original function, I'm not evaluating the derivative. I'm not looking for whether the function's increasing or decreasing. I'm just trying to figure out like how high or low does the function go, and that is controlled by f of x. So I've got this in here. Now I can go to the table. I'm evaluating this at -2, 0, and 1. At -2, I have -0.8. At 0, we have 0. That you probably could have easily evaluated by hand. And at 1, we have -0.125. The one thing I would actually say is, in this case, I actually encourage you to use your calculators. If you do this by hand, sometimes you end up getting fractional answers, and then you have to compare them to see which one's smaller and which one's larger. So sometimes it's easier to just put it in your calculator and get the decimal equivalents. Okay. All right, so now we can make some conclusions. We're going to look at these three values, the endpoint values, and then that middle point value that's sitting at the critical number. My uncle passed away, and I requested the clock. That was like the one thing I wanted, and I love the clock. It's about to chime so many times, which will lead you to understand how late I'm recording these videos. So it used to be my grandma's clock. Okay. All right. Notice that -0.8 is actually a smaller value than -0.125. It's more negative. You know, you can always just look at the number that comes after the decimal. Maybe it would be helpful if I put the 0 in front of the decimal. But the smallest value you're actually seeing here is -0.8. So this would be our absolute minimum. So the absolute minimum occurs at the point -2, -0.8. And then the maximum value, the highest of these three numbers, the largest one, is actually 0 because it's not negative. So the absolute maximum would occur at this point, 0, 0. And that's it. Now, I would like for you to leave your answers I would like for them to be exact. Now, in this case, 0.8 is a terminating decimal. So that's fine. In the future, though, if you ended up getting a decimal that was not terminating, I said that it was nice to have the decimal equivalent so that you can compare the numbers and see which one's larger or smaller. But I would want you to plug this into the function to determine the situation there with the actual exact value. So if I'm looking at the denominator, -2 squared is 4. 4 minus 9 is -5. And then in the numerator, -2 squared is 4. So my actual value here in fractional form is -4/5. There's a way to get your calculator to do it. I recently had a student show me that their calculator was only giving them fractions in the table. But I'll show you what I'm doing here. I think it was, I don't remember. I'll have to look and see if I can force it to do that again. I don't know. I'll have to see. So a student brought me a calculator that was only giving fractions in the table, and I'd never seen that before. I'll have to look. Can't remember the setting. Either way, we have a conclusion here. This is the answer. The absolute minimum is at x equals -2, and the value of the minimum is -4/5. And the absolute maximum occurs at x equals 0, and the maximum value is 0. Now, really what you're looking at, and we've already put this into our graphing calculator. If you actually look at the graph of the function, remember that we're not actually looking at the whole function. We're only talking about the interval from -2 to 1. Now, we could always isolate that here, but essentially we're looking at -2 to 1. If you want to see what that looks like, I can set my window such that x goes from -2 to 1. And we'll graph it. And it's kind of hard to see. We could always adjust our y value, because right now this looks very shallow because we have so many points here. But let's say we adjusted our y value to have a y min of -1 and a y max of +1. I mean, these values are going to stay in that range. And then we'll graph it. Now it's a lot easier to see what's happening. So from x equals -2 to x equals 1, you're seeing that you have the top of the hill here, which would be that relative extrema that we found from the critical number. That would be the maximum value. And then you can see that the graph starts to decrease on the right, and it starts to decrease on the left. When we look at the endpoint values, we're looking at these cutoffs where I cut it off on the calculator because we only looked at it from -2 to 1. But you're looking at the function value here on the right and here on the left, and you're trying to determine which one's lower. The one on the left at -2 goes down further. That's the smaller y value. The one on the right is, yeah, it's smaller than the maximum, but it's not that low on the graph. So that is kind of a pictorial representation of what you're seeing in the data. I'm going to put another example here, a polynomial function that we'll work on next. This one won't take up quite as much space, but again, if you want to move to the other side of the page, if your writing is a little bit larger, you might need to do that. So this is going to be example 2. F of x equals 1/3 x cubed minus x squared minus 3x plus 2. And this is going to be on the interval from 0 to 6. One thing you might want to notice, and we did this for the first function, was we talked about the continuity of the function on the interval. We cannot use this if the function's not continuous on the interval. But example 2 contains a polynomial function. We're not dividing by 0 anywhere. We can't. We're not taking the square root of a negative number. We would say that this function is continuous for all real numbers. f is continuous on the interval from negative infinity to positive infinity. Okay. So now that we've verified that that's true, again, we're going to go through the process of finding critical numbers using the first derivative, and then we're going to evaluate the function at the critical numbers and the endpoints to determine the absolute extrema. So let's find f prime. So this is going to be 3 times a third, which is just 1, x squared, minus 2x, minus 3. Now I need to set this either equal to 0 or say that it does not exist. It's never going to not exist. So if you want to make that note, that the derivative does not exist, never. Does not exist, never. It's a double negative, but basically the first derivative is going to exist for all values of x. So we don't have any problem values of x there. But we can determine that f prime of x equals 0 when this polynomial is equal to 0. Now this is a quadratic equation. In order to solve a quadratic equation set equal to 0, if you can factor it, factor it. Otherwise, use the quadratic formula. So I'm looking for two numbers that multiply to -3 and add to -2. And those values would be -3 and +1. And if that's true, then I know that either x equals 3 or x equals -1. Now, it always reminds me when I have more than one value to double check the interval and make sure that the values that I'm including are actually included in the interval. So I have been given the interval from x equals 0 to x equals 6. X equals -1 is not in that interval, so we don't need to test it. We could say that it's not in the interval from 0 to 6. Now, I do want to see that you found it, and then I just want to see that you just tell me it's not in the interval. So don't just leave it off and don't erase it. Don't do that. So I have one critical number that I'm going to test here in the interval, and then I'm going to look at the endpoints. So again, I'm looking for the value of the function because it's telling me how large or small the y value is, not the value of its derivative. So I'm looking for f of 0, the first endpoint, and then I'm looking for f of 3, which is our critical number, and f of 6, which is the right endpoint. I'm going to evaluate the function at all three of those values. 0 is the easy one, 0, 0, 0, 2. Fine. If you want to use your calculator to find the other two, that is fine. Whether or not you want to do it actually using the graphing calculator is also fine. You could always just plug it in. These values are positive, so if you just felt like it might be faster to just evaluate them both, then that's also fine. So we have 1/3 times 3 cubed. I'm evaluating f of 3 here. So 1/3 times 3 cubed minus 3 squared minus 3 times 3 plus 2 is -7. And then f of 6, I can do the same thing. 1/3 times, I'm just going to recall the last answer. I'm going to enter 6. Then I have another 6. 3 times 6 plus 2 is 20. So I can now state that the smallest of these values is the absolute minimum, and the smallest would be -7. The absolute minimum occurs at 3, -7, and the absolute maximum is the largest, which is 20. Now, it doesn't have to be the case that one of these absolute extrema is at a relative extreme value. They could both be at the endpoints, or it could be that you have more than one critical number and none of the extreme values are at the endpoints. It's random, so don't feel like there's some pattern that you might be missing out on. That's not the case. Okay, so that was absolute extrema on a closed interval. Let's talk about absolute extrema. Good old absolute extrema of this function, f of x equals 2x to the 5th minus 3x squared plus 9. Now, for this one, we're not talking about a closed interval. I'm asking you, like, can you find an actual absolute maximum value and an actual absolute minimum value? Now, one of the things that you could do here, because I'm not giving you an interval, I'm going to say no closed interval is given. So that means that we're looking at the absolute extreme behavior on the entire real number line. Look for extrema absolute on the whole number line from negative infinity to positive infinity. Okay, now 2 things that we can do here. One of the things is just to continue, just to look at the function itself. So if I'm trying to determine what's going on with this graph, I can really think about what's happening to these function values as x gets increasingly large or increasingly small. So for instance, as x gets increasingly small and heads off towards, let's say, negative infinity, the behavior of this function is going to follow the behavior of the leading term. The lead term is the one with the highest power on the variable. So in this case, 2x to the 5th. Now, negative infinity to the 5th power is still going to be negative infinity. So multiply that by 2 and you still get negative infinity. So I would say as x approaches negative infinity, f of x also approaches negative infinity. Now, we sort of used this reasoning back when we were talking about finding limits at infinity in chapter 3. 3, yes. 3? 2? No, 2. Chapter 2. I always get confused because we start on chapter 2 in this class and it throws me. And then we can talk about what happens as x gets increasingly large. As x approaches infinity, this function is going to do whatever the lead term does. Infinity to the 5th is infinity. Multiply it by a positive number, and it's still infinity. So in this case, if we're going to negative infinity for the function values on one side, and then the function's going to positive infinity on the other side, it can't possibly be the case that we have any absolute extreme values. What you'd be looking for here is like, well, maybe you would have a situation in a different type of function where one side as x goes to negative infinity, maybe goes to negative infinity, and then maybe the other side also goes to negative infinity. If you know that both sides of the graph are heading down, something's happening in the middle. And what's happening in the middle would be where those extreme values would occur. But in this case, we don't know exactly what the graph looks like. We're going to graph it in our graphing calculators in a minute, of course. But we know that as x gets increasingly small, the function values are heading down. And we know that as x gets increasingly large, the function values are heading up. If we know that the function values are only going up forever and down forever, we have no possible way that we would have any absolute extrema. Like, it can't be. We could have some relative extrema happening somewhere in the middle, but we can't possibly have absolute extrema. So there's that. If you were to look at this in your graphing calculator, I'm going to graph this polynomial function. It's 2x to the 5th minus 3x squared plus 9. Okay, 2x to the 5th minus 3x squared plus 9. Maybe you can't hear the clock chiming, and maybe the sound is being muffled out of the background of my video. That would be great. So maybe you're like, what clock is she talking about? If you didn't hear the clock chiming, this is a good thing. All right, here's my function. I'm going to go back to Zoom 6. I might need to even adjust my zoom because who knows what kind of crazy values this graph might have on it. Oh, it's not super crazy, but already you're kind of seeing what we already wrote down. Like as your values of x go to the left, your values of y go down. As x goes to the right, y goes up. So you have this situation where in between, fill this out in between, you have something going on. You have relative extrema. So it's going up like this, like, ooh. something like that, obviously on a different scale. So you only have relative extrema here. I don't think this function would be possibly doing anything else in there, but you can always adjust the window to see, but it really doesn't matter because I asked you to find absolute extrema. So we have relative extrema only. So in some cases, you'll just be asked questions without being given an interval. And that's how you would look at that. It's mostly just kind of like what's happening to the behavior of the graph as x gets increasingly larger, increasingly small. Like, can we make a conclusion about a maximum or minimum value? We're going to do something similar now with a little bit of, with a rational function. So this is going to be f of x equals x over 1 plus x squared. And I'm not going to give you a closed interval. I am going to give you the interval from 0 to infinity. And we're not including 0. Remember, the parenthesis means that it's not included. One thing you might want to note, though, right away is look at your denominator. It can only be positive. No matter what x is, x squared can only be a positive value, and it's being added to another value. So the denominator can only be positive. That means that the domain of your function is actually all real numbers. So we are definitely continuous here on the interval from 0 to infinity. F is continuous on, I'll just repeat it, 0 to infinity. All right, there are no values that could possibly cause this denominator to be 0. So we don't have continuity issues on this interval or on any interval. If its domain is all real numbers here, we're going to just go ahead and make that statement. All right, so we know that. What we're going to do now, since we've isolated this to the interval from 0 to infinity, is we are going to look for critical numbers and determine at least if we can find some sort of value on this graph that might represent a maximum or minimum. And then we can talk about what's happening to the rest of the graph as x approaches 0 from the right and as x approaches infinity. So let's go ahead and look for a critical number first. If you're thinking like, well, why don't we do this kind of like we did the last one? Well, this one's going to be a little bit different because if we tried to evaluate this at 0 and infinity, well, at infinity, you would end up getting infinity over infinity, which is indeterminate. It's not infinity. And at 0, you just get 0. So you at least know that you have a value there, but you don't know is 0 maximum or minimum. So we're going to have to figure this out. So we're going to find the first derivative, f prime g minus f g prime all over g squared. So you'll have 1 plus x squared minus 2x squared divided by 1 plus x squared. Oops, I forgot to square my denominator, sorry. 1 minus x squared over 1 plus x squared. Quantity squared. Now I'm going to look for critical numbers. Critical numbers. Remember, the critical numbers are going to occur when the first derivative either equals 0 or does not exist. We already said that the denominator wouldn't possibly have any of those values, but we can look at the numerator. So this is going to be 1 minus x squared equals 0. You can factor this, or you can solve it using the square root property. If you use the square root property, you're going to say x squared equals 1, and then x equals plus or minus 1. I kind of like to factor it because students will forget to put a plus or minus sign on it. So you decide, but I'm going to go with this method, and we'll say x equals plus or minus 1 regardless. Now, I shouldn't have put a box around that so quickly because I'm already having regrets. I gave you a domain from 0 to infinity. And then I told you that -1 could possibly be a critical number. It was a lie, not intentionally. It can't be -1. So I must say the critical number can only be x equals positive 1, because x equals -1, is not in the interval from 0 to infinity. So get rid of that. And if you're looking for, to be complete about this, if you're trying to find values where the first derivative does not exist, we'll say none. The first derivative is going to exist for any value of x because the denominator cannot be 0. 1 plus x squared cannot be equal to 0. So we have that. Wonderful. All right, so we're going to have to look at a little bit more here than we normally would if we were talking about just finding extrema on a closed interval. One of the things that we already know, for instance, is that f of 0 is 0. Oh yeah, I think I already said that at the beginning when I was talking about the domain. Two things to note. So we're going to note, first of all, f of 0 is 0. We should probably also talk about what's happening at the critical number. So let's find f of 1. F of 1 is just the function value at 1. So it's just 1 over 1 plus 1 squared, which is a half. Now, I already know that 0 is less than a half. But the question is, like, do I have enough information at this point to conclude that 0 would be the absolute minimum and that 1 would be the absolute maximum? Because you don't know what's really happening with the rest of this graph. We do know that because 1 represented a critical number and because f of 0 was 0, we can start to get a picture for what we think is happening to the graph. So f of 0 is 0, occurs right here. And then we know that at 1, this is going to be scaled out kind of crazy. This will be 1. We know that the value of the function is a half. What we're trying to figure out is what conclusions can we make about the rest of the graph? Now, I'll tell you one thing. When you find a critical number, that means that that is the only place. In this case, you only had one critical number, so that can be the only place where you have relative extrema. It's only going to occur at places where either the first derivative was 0 or did not exist. So this value right here has to be the maximum. You're not going to come up with any values that are larger than that. We know that because the critical number has to represent the top of the hill. Now, you don't exactly know what's happening in between these values, how rapidly it's changing. You don't know anything about the concavity, but you know that it can't possibly dip down and come back up again. Otherwise, we'd have another critical number, but we don't. It must be the case that our function goes up. Now, officially, I'm catching myself here because we can't actually include 0 in the function. You know what? It's driving me crazy. I've been thinking about this for like a minute and a half now. We still want to kind of put a point there, but it doesn't actually exist on the graph because it's not included. So you know what? It'll make me feel a lot better if we leave that circle open. Sorry, I should have thought about that initially. I went to town graphing points. Okay, so we know that we have this relative extreme value here at 1/2. We know that the function value at 0 is 0 because we know the function must be increasing as it heads from x equals 0 to x equals 1. So we have enough information here to definitively state that we have an absolute maximum at 1/2. We got that absolute maximum. It has to be. You have to make some logical conclusions here. There's no other point that could possibly be higher than that because we would have to then have another critical number. We don't. The graph is not going to turn down again and go back up. It can only come down and stay down. Now the question is, however, how far down does it go? I mean, are we going to be dipping into values down here below the x-axis? What's going to happen to the function? So in order to do that, we need to make a conclusion using the fact, we can use a couple different things. One thing we need to think about is the fact that this graph actually has a horizontal asymptote. So as x gets increasingly large, we can think about the value that y must possibly head towards on the graph. So let's look for your horizontal asymptote. Now, I pulled this back up so you could see your original function. Remember that I told you, if you would like, you could rewrite your original function so that you had the same degree in the numerator and denominator. So the whole idea of that is that you can always use that ratio of lead coefficients rule to look at your horizontal asymptote. So I took our original function f and I only changed it by just writing 0x squared as the first term in the numerator. And once I do that, well, now I can use the ratio of the lead coefficients. The horizontal asymptote would be equal to y equals 0 over 1 and y equals 0. So it must be the case that this function approaches it approaches the x-axis as x gets increasingly large, but it's not going to touch. Now, if you're thinking like, well, how do I know, like, how do I know it doesn't go back down and come back up? It can't. You already found the only critical number. It can't turn again. It's going to increase and then it's going to decrease forever. I think I messed up the concavity on it, but this is kind of what's happening with the graph. We're going to graph it in a second so you can verify. Now that we have that, though, let's talk about the absolute minimum. I feel like the absolute maximum makes sense. And again, I'm making some very logical conclusions here. This is a little bit of a harder problem because of that. Notice that we did not include 0 in the domain, or in our interval, sorry, not in the domain, in our interval. If I had included 0, I would be able to come up with an absolute minimum value. I would have said, okay, well, the absolute minimum is 0. We didn't include 0 in the interval. The interval goes from just above 0 to infinity. Now, look at this sketch. A lot of times we just sketch if we're not really sure what's going on. We're approaching the x-axis here, but we're not actually touching it. Same on the right. We're going to approach, but we're not going to touch. There's no absolute minimum value here. You can't touch the x-axis, and we don't have another definitive point anywhere between there. We only have values we can approach, we can get really close to, but we can't get there. So we're going to say that we have no absolute minimum on the graph. You can approach y equals 0, but never touch. So it's a really good problem. Let's see. Let's look at this in our calculators just to see how close our sketch was. Like I said, I think my concavity might be off, but let's look. So this is going to be x divided by 1 plus x squared. Okay, I'm going to zoom 6. I'm not looking at the left-hand side of the graph. Do you hear the clock chiming? My husband was like, this clock is, I don't like the chiming. And I'm like, why would you not like the chiming? All right, let's adjust our window to go from, let's say 0, I don't know, 0 to 10 probably is good enough. We have to start at x equals 0 just because we're not including anything to the left of the y-axis. And then I would even say we don't need to have too many y values. The highest y value we're going to see is at 1/2. So maybe go from, you can just go from -1 to 1. You see, that's still more than we need. Okay. So this is what the graph looks like. It sort of looks like the picture, but yeah, my concavity was off a little bit, but that's what it looks like. Now you can see how you don't actually have any absolute minimum value on this graph, but we do have that absolute maximum value. So that one's a little bit tricky. All right, now let's look at this graph and we'll see if we can identify any absolute extrema from the graph. All right, so again, if you want to think about it as scanning from bottom to top, feel free. That's just what I do. So I start at the bottom. I'm like, oh, wait, I have a lowest possible point, and it occurs right here. And it's a filled in circle. So that means the point actually exists on the graph. You can attain it. So I'm going to say that this is an absolute minimum. Now scan up. So I started at the minimum, and as the y value increases, I'm heading up. All right, I got this open circle, heading up again. Now I'm looking at this open circle on the left, but I have another value that's higher. And I'm like, oh yeah, this looks like the absolute maximum, right? Right? Actually not. For the same reason we didn't have an absolute minimum in this situation, same idea. We can get close to a value, but we can't attain it because it's an open circle. An open circle says that you can get infinitesimally close to the value, but you can't touch it. If you can't touch it, you can't have an absolute max. It's not a definitive value. Not an absolute max. So the difference is that we have an open circle here. And the bottom absolute min, we had a closed circle. So we can attain the point on the closed circle, but we cannot attain the point on the open circle. So a little bit tricky there, but I think you can do it. Right. Oh no. If I could hear you all right now, there would be this groan of like, oh no, word problems. That's all right. Word problems are good for us. By the way, in section 4.5, all you're going to see is word problems. Really sorry to have to tell you that. But the ones that you're going to see in 4.4 are super straightforward. No big deal. The cost of manufacturing tennis rackets per day is, I'm going to give you a cost function. C of x equals 400 plus 4x plus 0.0001 x squared. I would be remiss if I didn't give you a cost function without a whole bunch of zeros behind the decimal point, right? I'm going to double check it now. Yes, 0.0001 x squared. Okay. Each racket can be sold for P dollars, where P is related to X by the demand equation. I'm going to give you that also. P equals 10 minus 0.0004 X. Okay. That's P. P looks a little not P-ish. Okay. So P is related to X by this demand equation. Excellent. That's a 10. If all the rackets manufactured can be sold, find the daily production level to maximize the profit. I did not give you a profit function, but you learned about how to find profit functions way back when in chapter 2. So let's build a product function for ourselves here. I said product, sorry, but a profit function. All right. So remember that we talked about the fact that you're only going to turn a profit if your revenue minus the cost is positive. So the revenue is how much money you generate from sales, but then you also have to pay for, the costs of manufacturing and the costs of, your employees and all that stuff, the cost of your facilities, equipment. So your profit, P of X, is going to be equal to the revenue, R of X, minus the cost. So this is from chapter 2. From chapter 2. So if you're thinking like, okay, fine, this is good. She gave us all of this information, right? She didn't. She got you close. I gave you a cost function, but I didn't actually give you a revenue function. I gave you the demand equation, but remember that in order to find the revenue, you're going to take the, you're going to multiply this demand equation by X. So we said it's basically just the price multiplied by how many you sell. That's going to be the revenue. And remember, P is the cost, or I want to say the cost because that's confusing with our cost function. But we're talking about P in dollars, and this is the amount that you're going to sell each racket for. So if we're talking about P dollars, then this is the amount of money you're selling each racket for, 10 minus 0.0004x. And you're multiplying that by X to multiply it by the number of rackets that you're selling. So the price for each racket multiplied by X rackets. I never actually stated cost of manufacturing tennis rackets. Yeah, so I guess I didn't actually say X was rackets, but I think that's implied with the function. Okay, so the revenue is going to be P times X. Don't get P mixed up with your profit. P, this is the price. P dollars times X. All right, so let's go ahead and find that. So P of X is going to be this price function, 10 minus 0.0004x times X. If you wanted to do it in the other order for your distribution, that might have made more sense to you. That's fine. Minus the cost function. I'm going to have to distribute this minus sign into the parentheses. So I'm going to make sure I remember to put my parentheses on this function. 0.0001x squared. And I'm going to simplify to get a simplified profit function because you know where we're going with this, the derivative. Okay. P of X is, so this is going to be 10x minus 0.0004x squared. I'm just multiplying in at this point. Minus 400 minus 4x minus 0.0001x squared. And then I'll simplify whatever else needs to be simplified. I like to write my functions in descending order. So right now I have negative 0.0004 minus 0.0001, and that gives me 0.0005. Oh, negative. I almost forgot about the negative. X squared. So again, you can just, negate the zeros and just take -4 minus 1 to get the -5. Put the zeros back on. I said negate the zeros. It wasn't supposed to be a pun, but I guess it turned out to be one. Plus 6x minus 400. Now, we found a profit function, and you were told to maximize profit. So this is what I'm going to maximize. Now, don't panic if you're like, I have no idea what you're talking about, maximize product. Well, I said product again, profit. What we're thinking about here is this really just essentially represents some function, and it's the graph of some function, and you're trying to figure out where the maximum and minimum values are. If you're, well, really the maximum value. If we're trying to maximize the profit, then I just am trying to figure out what value of X will lead me to the largest value of P. In order to do that, I'm going to have to take the derivative, and then we'll evaluate. So let's take P prime of X, and I'm going to multiply all of these values. So I've got negative 0.001 X plus 6. And this is a polynomial. I don't need to worry about the first derivative not existing, but I do want to set it equal to 0. So this would be P prime of X equals 0. I know I'm doing it in reverse. So now I know that 0.001x equals 6, and I can take 6 and divide it by my answer to get 6,000. Well, remember 6,000 would just be the number of rackets. So I did not give you X. I gave you a C of X, and we said that it was about rackets. Cost of manufacturing, let's say X, tennis rackets. Just want to make sure that is in there and it doesn't get overlooked. All right, so we're going to look at this, this like relative extreme. And if you're wondering, like, well, don't we need to also look at the endpoints here? Well, what would the endpoints be? I mean, think about it. We're manufacturing tennis rackets. I guess you could manufacture 0 tennis rackets. But then do you think that manufacturing 0 tennis rackets would actually turn you a profit? So, I mean, looking at your profit function, if you let X be 0, you actually have a negative profit. Your profit would be negative $400. I'm surprised it would only be that amount. You would think it would cost you a lot of money to just get set up to manufacture 0 tennis rackets. Okay, so 0 is not going to be an option for us. We're not going to manufacture 0 tennis rackets, so you don't need to worry about that. And the other value that we would normally look at would be the upper endpoint, but I didn't give you a closed interval. I mean, I never said like the facility can only manage to make this many tennis rackets. I didn't say that. So you're assuming here that they're just going to make tennis rackets forever and ever and ever because they can. So we actually, if you were thinking about this, I'm going to formalize what I just said with some writing. I'm going to at least maybe not formalize it, maybe just jot it down. We don't have any endpoints here. No endpoints to check. X equals 0 means no rackets are produced. And we don't have a maximum value of X. Yeah, we would say we have no maximum number of rackets given. So we don't have a number of that we were cut off at. Sometimes you'll get that in a problem. Like, this is how much the facility can make. They can only make like 20,000 rackets a day, something like that. We don't have that in this case. So we're going to assume that 6,000 is the maximum because it is just the only place where we have the hill or the valley. And you know it can't be a valley because we started out saying, well, if we make 0 rackets, then we have a 0 profit. So it wouldn't make sense for us to go further down in profit as we started to generate these tennis rackets. So this is our conclusion here, and we're going to verify it by showing that it represents a max. I know logically we just talked about why that must be a maximum value. We can verify this using the second derivative test though. Now, we only did one example with the second derivative, the second derivative test. We did one example of it and it was in 4.2 and it was in part 2 towards the end. We said that if the second derivative of a function evaluated at the critical number was positive, then we had a minimum. If the second derivative evaluated at the critical number was negative, we had a maximum. Now, if you want to use the first derivative test, that's also fine. You can do a sign analysis and show that your function's increasing to 6 and decreasing thereafter. That would also show that you had a maximum. But if you only have one value to test, a lot of times it makes sense to use the second derivative test. And this is to verify X equals 6,000 is a maximum. So to do that, we'll take the second derivative. The first derivative was just, the function's a polynomial. So the second derivative is not going to give us any trouble. Notice, by the way, that the second derivative is a constant. and it's negative. If your second derivative is negative, and we usually say evaluate it at a point, well, there's nowhere to evaluate it. It's just negative all the time regardless. Second derivative is negative. That means that by the second derivative test, which again was in 4.2, we have a maximum. Okay, so you knew it had to be one or the other because it was a critical number. You were just verifying that it was a maximum instead of a minimum. So your maximum profit, going back to what the question was actually asking you to find, if all the rackets manufactured can be sold, find the daily production level to maximize profit. I'm going to actually find the max profit. The max profit occurs when X equals 6,000. And now we can just find that profit function and evaluate it at 6,000. So P of 6,000, you can put this into your calculator. I'll go back to my profit function here. Where is it? There it is. Here's the profit function. I'm going to use this one. Negative 0.0005 times 6,000 squared plus 6 times 6,000 minus 400. And you end up with 17,600, which makes sense. You're talking about a profit selling tennis rackets. So, oh, sorry. Maximum profit occurs when X equals 6,000. P of 6,000 is 17,600. So you can always ask yourself, does this make sense? And I think that makes sense as a profit for selling tennis rackets, especially like 6,000 of them. I mean, a lot of profit, really, when you think about it. Maybe I should get into the tennis racket business. All right, that's all I have for you in this lesson. Next time we'll do more word problems and more optimization. But until then, you can work on these and enjoy. Have a wonderful rest of your day.